So welcome everyone to our monthly invited lab talk series. So this is the first talk in the new semester, and we're really happy to have Günter Wallner as our speaker. So Günter did his PhD at University of Applied Arts in Vienna, and he was then later on appointed as an assistant professor at Eindhoven University, and he's also still an adjunct professor at Ontario Tech University. And starting with beginning of March this year, Günter is now a professor for game computing at the Institute of Computer Graphics, and we're really happy about that. So welcome, first of all, Günter. And in his work, Günter focuses on understanding player behavior in games, and he's also interested in researching methods to derive actionable insights for game design and development. And now we're all really curious to hear what you have to say about your research topic. And the title of your talk is Visualization of Mixed Playtesting Data. Günter, the floor is yours.
Thank you. Thanks for the introduction, and welcome everyone. Glad to see that so many people could make it. I'm just going to quickly share my screen. So I hope you should see the slides by now. So yeah, as Mark already said, I would like to talk about visualization of mixed playtesting data today. And I also have prepared a slide with a short introduction, but I think Mark already covered most of it as well. So my background, or the area I have spent most of the 10 last years, was in games user research and games analytics. And I'm especially interested in finding methods or exploring methods which help to make sense of collected player data. And within that area, I'm especially interested in visualizations which help the analysis of those data sets, which can become very large, and they can also be coming from different data sources, and that would be the topic of today. On the slides, you can also see a couple of stuff I have been working on in the last years, going from movement analysis down to social network analysis of player networks, for instance. But today I would like to focus on a specific subtopic, namely playtesting. So when we ask people what game development usually entails, then most people start with like talking about computer graphics, about the sound or the artificial intelligence of the non-player characters, for instance. Or they also talk about a game's design in general. But what really comes to mind at first is basically the player, which is on the opposite side of the screen. And of course, games are made for players. So it's of course interesting to see what players think about it. And on the other hand, players have a huge impact on a game's success. So it's important that it matches what players expect or would like to see. And in that sense, playtesting has become very common in game development. And playtesting can be defined as the act of observing someone play your game with the intention of understanding that player's experience. And observation here has to be seen in the broad sense. So it's not just observing someone, but observing could also be by tracking data, for instance. So as said, playtesting has become quite an important part of game development nowadays. The issue here is that, of course, measuring or collecting data is one thing, but on the other hand, you also have to analyze it to basically make sense of it and derive information which you can use for the further game development. And this can be quite challenging because the data can really become quite large, and also most of the time, playtesting uses different types of data sources to collect the data. So to inquiry about different aspects of a player's behavior or experience. So it's, for instance, quite common that you combine a video recording and observation with interviews and in-game tracking of data. And you usually want to combine those sources because only then you can contextualize them and better use them actually. And visualization has become an important tool in this respect to efficiently analyze the collected data. So the heat map is probably one of the most used visualization in that context. And today I would like to specifically focus on triangulating different data sources to help with a better contextualization. I will also talk about how we can aggregate the data and how the actual representation of it may impact the interpretation of it. So I'm basically like a big proponent of information visualization because it, of course, offers many benefits. So I won't go through that in detail, but just like a few points which make it very valuable in this respect. So first and foremost, visualizations make very good use of our cognitive and perceptual abilities as humans. And this allows us to quickly and more easily perceive information if represented visually. And in that sense, they also allow us to observe large volumes of data and to see patterns which are inherent in the data. And of course, like as we are talking about visualization, digital visualization, computer supported, it also offers ways for interactivity so we can view the data on varying levels of detail. And lastly, and that's also quite valuable in the context of game development, is visualizations are also a very suitable means to communicate the findings, especially in teams where people have different background expertise. And in game development, this is quite common. So all those benefits also make visualization a very good tool when working with that specific type of playtesting data. So I already mentioned it a little bit earlier. We have quite a lot of different sources and types of playtesting data. But for the purpose of this talk, I would like them to group them into three main categories. And the first one would be, we are dealing with discrete events. So basically we have events which happen at a certain point in time in a game. This could, for example, be a player collecting an item, picking up a medikit, these kind of things. But of course, it could also be things which are external to the game. It could be a coding or observation which has been made while observing someone play. Secondly, there is movement data, which I listed separately here because it's so important in so many games, because most of games have a spatial component or a movement-driven gameplay. And the third type of data is like continuous data, so data which changes frequently in the course of the game. So this could, for example, be the health of the player. It could also be like data measured through a sensor, physiological data, for instance. And here, I think it's very important to emphasize that it's always good to visualize or interpret the data in relation to player movement. So you have a sense of where something in the game environment, something happened. So throughout the talk, I will rely on data which we collected from Infinite Mario. And Infinite Mario is a public domain version of the famous Super Mario Brothers game. So I assume many of you are familiar with it. But just to give you a sense of how the gameplay looks like, I will attempt a short live Mario session now. And let me just quickly switch. So that's the implementation of it. And in the game, you are controlling Mario. And it's composed of different levels. You basically have to traverse from the left to the right. So you can go, so most of the movement is to the right, but you can also go back, of course. And then you have those enemies running around, which you need to avoid. Otherwise, you are losing a life. So let's see. And then you have those coins here, which you can collect. And you have those different kind of blocks, which you can bump. And in some of those blocks, power-ups are, for instance, hidden. And that make you grow in size or allow you to throw firebolts, for instance. Let's see if something is inside here. No, but that's basically it. And then you try to reach the other end of the level, and then you proceed to the next one. And we conducted playtesting sessions with it. So we asked a couple of players to come to the lab, and then we video recorded them while we were playing the game. And then we annotated those playtesting videos. And these annotations are basically handled as discrete events. So those will be displayed in the visualization as discrete events, which happen at a certain point. We also instrumented the source code of the game, so to track the in-game data. And of main interest today is the movement data. So we track the in-game position of the Mario character. And we also attached everyone to a GSR sensor and measured physiological responses. So in particular, the arousal values. So how excited players have been at certain parts in the level. And this kind of data will be treated as continuous in the following. And so here on that slide, you can see basically one way to visualize the data. So the data of each player is represented individually. The paths you can see are the individual player trajectories, and those have been color-coded. And the color coding reflects the GSR data, so the arousal values. And yellow would correspond to low arousal, and red would correspond to high arousal. And because we have mapped it to the paths, the values are also shown in relation to the position of the player in the game. And the overall hue of it already provides some impression of the overall arousal in a certain area. So for instance, in this area around here, we have mostly yellowish colors. So people had quite low arousal. And it's also because this is quite a safe area here. So that's not surprising. There are no enemies here, and if you miss a jump, you cannot fall to death in that area. So that's really easy to navigate, basically. But if we look a little bit more to the right, we can see a part where we could rather have a majority of reddish values. So players got pretty excited here. And that's because they had to basically run and make a long jump to make it over the white gap, to not fall into the pit here. The speech bubble or text bubble you can see here is basically a comment which has been made by a player during the playtesting session. And again, it's shown in relation, it's shown exactly where the player has been at that point in the level. So the environment, again, provides a certain context for interpretation of the comment. And the small icons, the white ones, you can see scattered across the image, are basically the discrete events. So that's the insights which were inferred from the playtesting video. And those were basically grouped into different kinds of categories. Like if someone had missed a jump or had trouble making a jump, these kind of things. And so generally, I would say it's already quite a nice overview of how people played through the level here. But of course, those individual representations are soon quite limited. And we have several drawbacks. So for instance, we have occlusions. Like in that excerpt here, we have all those small icons which are in near proximity to each other. So that makes it basically very hard to read those icons, or even impossible at some points. Of course, it's also prone to visual clutter. So, and this again makes it very difficult to read and interpret in places. So for example, here on that excerpt, there was a lot of jumping going on in that area where people were trying to bump those blocks, likely to see if a power-up or something is inside. And this resulted in quite a visual mess, which makes it very difficult to comprehend what's going on here. And you might think that's only an issue if we have a large number of players, but this is actually only based on 6 players. So this is a problem which we face quite frequently and quite soon. And since we are talking about also about movement, it's also like providing a misleading impression of the frequency or the amount of movement. So if you look in that area here, you just see one line. So it somehow makes the impression as just one player moved along here. But actually all the players moved exactly along the same path. And because of that, all the lines are drawn on top of each other. And now we also have occlusions again, because now we can only see the arousal values of the topmost player anymore. So these are just a couple of issues. And in that sense, like aggregation can be very valuable to achieve a better non-cluttered representation of the data, and also to highlight general patterns and to give users an impression or a general idea of how players behaved. So in the following, I would like to show you one approach we came up with, and which uses 3 different aggregation techniques. And those techniques can be applied to the common types of playtesting data I showed earlier: discrete, movement, and continuous data. And they can also be used in combination or individually, depending on what you are interested in, basically. And of course, since we're talking about mixed playtesting data, it's also applicable to these kind of data sets. So in the first step, we are basically taking care of the discrete events. So we apply a clustering algorithm to the positions of the discrete events to group events of the same type within a certain vicinity together. And then we represent those groups using a single icon, where the size of the icon reflects how often that particular event has occurred. So for example, that icon represents troubles with jumping, for instance. And the idea here is to reduce the amount of the icons while also giving a better impression of how often something has occurred. In the next step, we basically take care of the movement. And for that, we subdivide the level into small non-overlapping cells based on the player trajectories. And the user could, for instance, also influence the size of the cells here, which also gives some flexibility in the level of detail the final visualization will have. And then we are replacing those individual lines of all the players with line segments showing the transitions between 2 adjacent cells. And the width of the line reflects the amount of transitions. And that way, the main paths are more accentuated than divergences from it, for instance. So again, the idea is to reduce the amount of information, or at least to aggregate it to reduce the visual clutter. And lastly, we use the subdivision we created for the movement analysis and reuse it for representing the continuous variable. And in that case, it shows the average arousal value in a certain cell. So again, the more reddish it becomes, the higher the arousal has been in that area. And this way, the continuous variable is also again visualized with respect to the player position to provide the context for the interpretation of it. So if we put all of this together, we end up with something like here, where you basically can see the aggregated icons showing the events. We can see that the main path has been around here. We have the thick lines here, and we also have the arousal with respect to the movement. And here we also added transparency to the visualization to accentuate the cells in which the main movement activity has taken place. So you can see the cells along the main path are more opaque than in areas with less activity, for instance. So yeah, so we had this visualization, and then of course we were also interested in seeing what how useful it is perceived. And so we did an evaluation, and we reached out to 9 experts from the game industry, and we basically sampled for different roles with people having different expertise and also having a different visualization background. And the main goal here was to basically assess the usefulness, but to also compare the aggregated visualization with the individual representation I have shown at the beginning of the talk when introducing the Mario game. So in terms of procedure, we basically started with some semi-structured interviews to better get to know our participants. So we inquired about their background and experience with playtesting. And then we basically showed them the non-aggregated, the individual visualization and the aggregated visualization, and allowed them to interact with it for a certain amount of time to familiarize themselves with it. And after that, we again continued with the interview and checked about their thoughts. And we were also asked to perform certain tasks with the visualizations. So for example, we asked them to locate areas where players had trouble making a jump or where players have died, for instance. And all of those interviews were recorded and then transcribed for later analysis. And so based on that analysis, I would just quickly like to go through some of the results, and I would like to focus here on the aggregated visualization. And I have grouped them according to different categories. So first category would be the readability of the visualization. And here the aggregated one was better received, much better received in terms of readability than the not aggregated one, because people thought that the visual elements were more readable, they were better distinguishable from each other because the representation was less cluttered, the icons were aggregated, and the size of the icon reflecting the amount, and also the thickness of the lines, making it clear where the main paths have been, but also where the divergences from it have been. On the other hand, participants were a little bit concerned about the larger icons because they thought they would occlude too much from the level environment. Generally, participants did also not face any issues with interpreting the data correctly. And the visualization was perceived as clear and not ambiguous here. And we especially like the clear overview of the level and the interpretation of the continuous variable. Again, the main issue here was caused by the larger icons, but also by the color-coded cells, which also partly occluded the level environment, which resulted in a certain loss of context. And experts repeatedly got back to that. So that loss of context was a reoccurring theme in the evaluation. In terms of being informative, so if the visualization is able to provide new and interesting insights, our study showed that the aggregated visualization was especially deemed useful in areas with high activity. And that's also because these are the areas which are prone to visual clutter when representing the data individually. So this is where the issue appears at first, basically. In terms of accuracy, so we were also interested if the data is represented accurately enough to actually draw conclusions from it. And to our surprise, and that's really surprising in my view, the experts did not talk much about it, and we were also not concerned with respect to the aggregated visualization. And this is surprising because, of course, every form of aggregation goes also hand in hand with a certain loss of accuracy or a certain loss of detail. And the experts were actually not bothered by that at all. However, some questioned the accuracy of the visualization when the data which has been shown in the visualization did not match the expectations we had. So just one example, we had one expert who really started to question the accuracy because he just could not believe that the player was dying at a certain point in the level. And because of that, he thought that the visualization does not represent the data correctly here. Of course, all those results with terms of accuracy must also be considered in light of the tasks for which the participants considered the visualization useful. And here it was mainly considered effective for identifying main issues, but also for using it to report those to other people in the company. And lastly, we looked into the aesthetic appeal of the visualization. And again, here the aggregated one performed considerably better than the individual representation. People thought it's more clearly differentiable and perceivable due to the contrast in color and due to the aggregation itself. Some, however, still perceived it as a little bit noisy, especially in areas with high movement activity, because these are the areas where you have a lot of cell transitions, and then you still have a lot of the individual blue lines, for instance. So this brings me then to the second part I would like to discuss. Because when we created the visualization, we of course had made some specific choices regarding the visual design. So for example, we changed the transparency based on the amount of movement which had happened in a cell. So if you recall from earlier, cells were more opaque if a lot of movement happened, and cells were less opaque if movement activity was low. And we also made the decision to use a single color for each cell. So we applied basically a flat shading to it and to have a constant color. And so we were wondering if these choices actually influenced how people interpret the data. And we felt that's quite important because if the visual design is inappropriate, then it might be misleading, and it can, of course, have a huge influence on the conclusions people draw from it. So people may even draw the wrong conclusions and then propose the wrong solutions to it, which can have a huge impact, also a financial impact, when we talk about game development. And so to To dig a little bit deeper here, we set up another study where we basically checked about the influence of the shading and of the transparency on how people read the visualizations. So we compared two versions of the shading. We had a flat shaded version and a smooth shaded one. For the flat shaded one, we used the constant color as I had before for the whole cell. And for the smooth shaded one, we interpolated the colors across the cells because we actually thought that would reflect the continuous nature of the data better than the actual flat shading. But as I will show shortly, that also resulted in increased uncertainty on behalf of the participants. And then we also created two versions for the transparency. So we had one version where we used the same opacity for all the cells, independent of movement. And we created another one where we varied the opacity based on the amount of movement. So basically the initial design we had. And then we combined those into 4 different designs. So we had the constant shading with variable opacity and with constant opacity. And then we had the same for the smooth shading. So once with variable transparency and once with constant opacity. And then we went back to our 9 experts, which we have used in the previous study, and did set up basically another evaluation with them. So we basically handed them the 4 visual designs and again allowed them some time to get familiar with it. And then we had follow-up interviews where we discussed their thoughts, the disadvantages and the advantages of the visual properties, and also the preference they had with respect to transparency and shading. Again, all those were transcribed and then further analyzed. And based on that, we compiled a list of benefits and drawbacks with regard to the 2 properties, so with regard to transparency and shading. And I will go through them in a nutshell now. So in terms of shading, the smooth shaded one was considered to give a much better sense of progression and thus also a sense of the pacing within the level based on how fast the gradient has changed. It was also considered more aesthetically pleasing, but at the same time, it made it harder for the people to extract extrema from the visualization. For instance, if you compare that red area here with that one here, that's less pronounced here. So that high arousal area is not as well visible as it would be here. And that's the interesting thing now. It was also perceived as less accurate because the interpolation made it appear more muddy. So in terms of the color interpolation. On the other hand, the flat shaded one mostly excelled where the smooth shaded one fell short. So it was easier here to see the high and low level extrema. The outliers were also better to spot and more easily observable in that sense. But on the other hand, the progression was now harder to see because now you had those hard boundaries between those different cells. So let's move on to our second one, transparency. So in terms of the variable transparency, it much better supported the readability of frequency and intensity and offered a better summary in the sense that the highly traversed areas were better visible than the less traversed areas now. And in that sense, it also helped to locate the focal areas of high activity, basically, because those were more pronounced. However, people also felt that information is lost, as the variable transparency now also affected the coloring of those cells. So now it's much harder to compare the different color values because it's influenced by the opacity now. And that made it quite hard for them to draw direct comparisons. And the constant shading, on the other hand, had much better readability. It made it easier to compare the values because now you had the same opacity everywhere. So it was only slightly influenced by the background image. And it also helped to locate outliers because those were not attenuated by the higher transparency anymore. However, it also made it harder to see those focal areas I mentioned earlier, because now everything had the same visual highlight because everywhere was the same transparency, basically. And so based on those findings, I would just like to reflect now on a few more high-level implications, which could also serve as a sort of guideline, so to say, for the design of similar data visualizations. The design basically had not to be underestimated impact on the perception of data accuracy. So, for example, the variable transparency combined with the flat shading was especially well received in terms of facilitating accurate data interpretation, while the smooth shading actually posed concerns regarding the data accuracy, at least in our evaluation here. Secondly, being able to interpret the data in a timely fashion is quite important, also when development requires fast iterative changes, which is quite the case when we talk about games. And here especially the variable opacity was helpful for providing a quick summary because it allows to easily observe those areas of high and low player activity. Outliers are also quite an important source of information when evaluating player behavior. And sometimes it's even of greater interest than what the majority of players does. So an outlier may have found a bug in the game, or he may have making use of a bug or something. So or found a shortcut which should not be fair. So those outliers are a very interesting source of information as well. And the variable opacity has increased the readability and the identification of those outliers by pointing to the regions where those have traversed the level, for instance. Layering of data can, of course, also be quite helpful because it allows to add and remove data based on the analysis goals or the task. But it's also important to consider that it may impede readability, like it was the case with the variable transparency, because there the cell-to-cell color coding was much harder to compare now. Of course, the information which is conveyed by the visual designs also needs to be clearly articulated. So it needs to be clear to the user what a visual property or what an element of the visualization conveys in terms of information. So if people don't know that, they cannot include it in their analysis, they cannot make use of it, and then it doesn't contribute to the insights they are generating based on it. And lastly, continuous data is very frequently in games because it's like all dynamic processes. And on the other hand, the aggregation is quite tricky of it because it's also time dependent to some degree, of course. And here, the smooth shading actually resulted in a loss of clarity on behalf of our participants, although it would actually represent the data better in terms of its continuous nature here. So to wrap up, I would just like to go through some general takeaways. First, of course, it's important to visualize the data because it's a good way to analyze it and comprehend all the information you have. But it's also important to keep in mind that the choices you make with respect to the visual design can also impact the interpretation of it. If possible, try to triangulate different data sources to better contextualize your data. As said at the beginning of the talk, when doing a playtest, you usually have many different sources to basically capture different aspects of the player. So like you combine the in-game tracking with thinking aloud to understand, for instance, why a player was doing something, which you cannot get by just tracking the in-game behavior. Also, make use of aggregation to reveal common patterns and to make the visualization more clean, but also ensure that the outliers are not disregarded completely, because as said before, they can be very valuable. So if possible, try not to average them out or remove them completely from the data set. And lastly, also keep in mind that different people have a different visualization literacy skills, and the visualization needs to, of course, match those skills so that people are actually able to interpret the visualization correctly. This is also relevant in interdisciplinary teams where people have different backgrounds and may have not so much exposure to the latest visualization techniques than someone may think of. And that's it from me today. Thanks for joining. If you would like to read a little bit more about the visualizations I've shown, I have put the references to the papers on the slide. And we also intend to release the dataset soon. So if you would like to use it for playing around or for doing something, we also have that up soon on GitHub. Okay, thanks for tuning in.
Thank you, Günter. I see some clapping icons, emojis here. That's great. We have, as usual, time for a couple of questions. Who wants to go first? Oliver, I see your hand.
Yeah, I don't know if anybody else wants to go first, but I do have some questions, or at least one question. Günter, the example that you have shown, like the Infinite Mario game, is relatively simple. It's like 1D and player behavior options are very limited. How would you think that your research can be extended to more state-of-the-art, say, action-adventure games like Far Cry or Cyberpunk, which are significantly more complex?
Yeah, I think that's like connected with the third dimension. Like, of course, Super Mario is a 2D game, so you just have X and Y basically. But also many of those 3D games are basically just 2D in nature, so you can often very much just project it top down, for instance. If like games are really using like a multi-level architecture, then I think it would need to be extended to 3D. And you could do that with those techniques I have shown, because you could do the tessellation for the player movement is based on Wallner cells, and you could extend that to 3D cells basically.
But I think it's not just a matter of 2D or 3D, but it's probably a matter of what options as a player you would have. Like in this Infinite Mario game, you can, you have 3 options: go left, right, and jump. And I think in more sophisticated games, you simply have just more player options, no matter if you play in 3D or in 2D. So how does that, that scale
Yeah.
if you would go for a visualization approach to understand player behavior?
Yeah, so that's more connected with the gameplay options then. Yeah, that's the second part of the equation. Of course, that like you cannot add more and more because then again you have the issue of clutter. But it's sometimes you do not always need everything always. So you could like filter the respective data you would like to see or you would like to assess for a given goal. So if you if you would like to focus on movement patterns to see if people navigate through the level correctly or if they are getting lost, then you could just focus on a specific subset of the data. So if that answers your question.
Yeah.
Okay. Who wants to go next?
There's a question in the chat, I think.
Okay, let me check. Yes, so a question from Martin Stockinger. Are you involved in practical development project? How is practical value derived from your work? Is game testing visualization a fixed element in AAA titles today, AAA titles?
So yeah, so like so what I have shown here was not part of an actual development project, but I have been involved in some of these where we basically applied those techniques to help the designer improve the actual level design. So yeah, so in that sense, there is practical value of it because you influence the game development. And with respect to visualization, so I would say partly. It also depends like on the company and so on. But I think it's getting increasingly more used because the data size also gets increasingly larger. So it's quite easy to have gigabytes and terabytes of data, and then you need some sort of visualization.
Mm-hmm. And can you talk a bit about how industry is working? Are they doing this kind of research internally, or are they collaborating on this kind of analysis level? So are they present at KaiPlay? So I've seen that you're the general chair at the conference KaiPlay. Is industry present there? Are they investing actively in this kind of research?
I think there are two parts to that. Of course, the larger companies have their own games user research departments. Mm-hmm. And it's also very often very confidential data they're dealing with. But smaller companies who cannot afford basically own teams or something are often quite approachable with respect to collaboration, for instance. And I think it's more and more. So I think the connection between industry and academia is getting more frequent in that respect.
And does the community have access to some public benchmarking data or something like that?
Yeah, there are some data sets out, and that also gets better and better because more and more games are actually releasing data about player activity.
Thank you. I see that there is another question from Richard Küng. Richard, do you want to speak up and raise the question yourself?
Yeah, hi, I'm Richard. Very nice talk. I'm curious about like statistical aspects, like most notably outlier corruption, like players that are outlandishly good or bad. How do you deal with them?
Yeah, so like that work is not statistical in nature. What I have shown, that's like a pure visualization for exploration. So in that sense, it did not have any corruption on the results here. But of course, it's like if you're doing some statistical data mingling or something, then you have to be aware of it. And then what I have just said might also not apply directly to it, right? Because like if you talk about certain clustering techniques, they are quite, responsive to outliers, for instance. So it could make the conclusions also incorrect in that sense. So I think, again, it's like a little bit on the analysis goal. And the other thing, of course, is you could specifically focus on those outliers and see if they behaved in a way which you would not have expected or something.
And have you seen something like that, like from a more practical perspective? Like,
I mean, like in 3D games, there is often the issues that people find a shortcut which they should not find. And then you can see that, for example, in the movement data. And that's also one part why you should not throw it away, because those are quite often the interesting ones.
yeah, thanks.
My pleasure.
So are you actively like looking for those patterns, not just visually, but using some pre-processing to find those and then take that into account in the visualization?
Yeah, so we have not accounted for that in this visualization, but that would be an option. So you could specifically mine those specific patterns, for instance, and again, highlight it more in the visualization, for instance. So if you're searching for something specific. We have done something similar with a graph-based visualization where we looked for subgraphs or representing certain behavior, for instance.
Okay, other questions? Thank you.
Yes, I have one. Thank you for your very interesting talk. So,
thanks for the talk. I have two questions. For the visualization of non-static backgrounds, like the coppers or the turtles running around, did you include that somehow? Because the rule will be different.
Yeah, so not in this one. This is up for future work here, but it's included like in the background image. So you have a sense of where approximately they have been, but not like exactly. But that's another interesting point, because it's like the response and cause and effect relationships. And that's also quite important in that context. But it's not in this one right now.
And another question to the rule, could you maybe re-explain why you choose the cell color and not the aggregated line color, like in the single paths?
Oh, yeah. Like, so we aggregated it per cell and used it as background. I think it's like harder to apply it to the line, because then you really have to be careful about the interpolation there. And the other aspect is, like, you could use the color coding, which was just blue in the examples, to represent another value again. So you could add one more variable on that here.
Okay, great, thanks.
Thank you. Patrick, you had a question?
yeah, but it was the second question that Francis, I think, asked. So thank you.
Okay.
Yeah,
Other questions?
The other aspect of it is you don't have to just use the average. So you can use much more, like you could also visualize standard deviations or something like that. So you have some flexibility here.
Anyone else? Maybe I can ask another question from a list. So most of the analysis, the visual analysis you've shown is post hoc. So after the players played the game. Are there also activities to look into how to use this kind of visualizations during playing the game, so that you see what others do and maybe like integrate that into the game somehow?
Yeah, I think that's more going into the player direction, like providing it to the players, I think, while they are playing. So that's something which is addressed by live companions, for instance. Like I think League of Legends has those live companions where they actually pull the data in real time and represent that. So yeah, this is something which is also explored. Not so much, of course, on, I think, for level design analysis, because yeah, here I think the live aspect is not so important.
Yeah. All right. Time for last question. Any urgent, super urgent last question? If not, then let's thank Günter again. So maybe I see some clap emojis again. Thank you. As I said, this was the first talk of the semester. For those of you who do the seminar in AI, we already looked at the list of participants and we noted that down. And the next talk will be given by Matthias Niesner from TU Munich, and he leads the Visual Computing and Artificial Intelligence Lab at TU Munich. And the talk is going to be on the 13th of April, and the exact time point will be on our website soon. Right, this brings us to the end of our session today. Günter, thank you so much. I think many students will have the chance to see you in the new courses that you're going to announce over the next month. And there is, of course, much more coming at JKU going into this direction. And we're really happy that you joined us at the Institute.
Thanks.
Well, thanks, everyone. Have a nice rest of the day. See you soon, at least next month, for the talk given by Matthias Niesner. Thank you. Bye-bye.
Bye-bye.
Thanks, Bart.